All right, so let's go ahead and go through some of these practice problems where we're going to talk about how the core valence radius model really comes into play here. And so the thing we want to consider is this. We want to remember that a positive and a negative, they are attracted to each other. And so electrons are attracted to each other. If there's, electrons and protons are attracted to each other. And so if there's two positive charges, this is going to be a greater force of attraction between that and the electron compared to one. The other option is if we have this situation versus this situation. And so this second situation here will be a smaller force of attraction because the electron is farther away. So the two things we want to consider are number of protons and the distance. However, there's actually a third thing we need to consider. And the thing we need to consider is if we have a proton here and an electron, what if there's an electron in the middle here? That electron actually influences the force of attraction between this proton and this electron. So this middle electron here will influence that force of attraction. If you were to remove this, there would be a greater force of attraction versus if you had that there. And so that's something that we want to keep in mind. Now, before we get started, I already have on, this is page 37 in your booklet, I already have these electrons and protons filled out here. And so what I want you to do is pause the video, and I want you to fill in these inner electrons, which the purple ones are the inner electrons, the purple dots, and then the blue dots are the valence electrons. And so, and I also added the number of protons there. So go ahead and, forgot this one there. Go ahead and pause the video, and I want you to make it look like this. And we're going to take this concept and we're going to figure out what this effective nuclear charge of each element is for the valence electrons. All right, so let's go ahead and talk about hydrogen and helium. So these ones are really easy. There's one proton. There's one proton right here, and this one proton does have a positive charge, so this valence electron experiences a 1+ charge because there's a proton there. And then helium, if you take a look, this one's also pretty straightforward. This one experiences a 2+, there's 2 protons. And so these electrons right here, those are attracted to the nucleus as if there's a 2 positive there. All right, so let's go ahead and talk about lithium. And so this is where things get a little different. And so what we want to do is, again, we're considering the fact that we're considering how the valence electron is attracted to the nucleus. So this is the valence electron. Now, these two right here, those are inner electrons. And again, those are going around the nucleus. And so when we think about this valence electron has 2 inner electrons. There's 2 inner electrons. And so if there's 3 positive charges, however, there's 2 electrons that are shielding the nucleus. And I'm going to go ahead and represent those by a 2 negative. So those 2 inner electrons are shielding that nucleus. So what ends up happening is when we subtract these, we will get a 1 positive. And so the reality is, even though there's 3 protons there, the outer electron experiences a 1 positive from the nucleus because there's 3 protons subtracting 2 inner electrons, giving us a 1 positive. Now let's go ahead and think about this for a moment. We're going to go ahead and do the same thing for beryllium. Beryllium has 4 protons. there's 2 inner electrons. And if you subtract them, you'll see that you end up getting a 2 positive. And so when we're thinking about the valence electrons, those 2 valence electrons there experience a 2 positive. Now, something I really want to point out here is that the valence electrons don't really affect each other when it comes to the nucleus because they're on the same energy level, and so they're not really blocking the nucleus from each other. And if you take a look here, this next one, 5 protons, okay, so there's 5 protons, and there's 2 inner electrons again, there's a pattern here, 2 inner electrons, and so when we subtract these, you end up with a 3 positive. And so what that means is that for these valence electrons right here, for these 3 valence electrons, they experience a 3 positive pull from the nucleus. Now, again, it's a pattern, so sort of start predicting what you think the next one's going to be. Okay, so there's 6 protons, there's 2 electrons, that's 4 positive. And so what that means is these valence electrons, instead of experiencing a 6 positive, they experience a 4 positive. And the reason why that is because there's 6 protons, 2 inner electrons sort of blocking the nucleus, and then that results in a 4 positive charge. What I'm going to do is I want you to pause the video, and I want you to I'm gonna write this all in really quick, and so after this pops up, I want you to pause the video here. So again, I just filled out that first row there, and what I want you to notice is, notice how that row, and when I say the first row, I mean the second row, so this second row here, but notice how all of them have 2 inner electrons. So notice how the inner electrons don't change in the row. So as you go across the row, notice how they don't change. And notice how the core charge changes, the effective nuclear charge changes. And what we're going to eventually get to is we're going to say, well, when we think about this electron or this electron, when we think about those 2 electrons, which one has a stronger attraction to the nucleus? And the answer is going to be this one right here. That's going to have a stronger attraction to the nucleus because even though they're the same distance, the valence electron on carbon experiences a core effective nuclear charge of 4+. And so there's a larger core charge, which means there's a larger force of attraction. But that's what we're going to get to at some point. So what I'm going to do now is let's go ahead and talk about this third row here, all right? Because again, there's more patterns to be seen. First off, this third row, everything in that third row, if you take a look at the inner electrons for all of them, and if you need a moment to pause the video, do so, but if you take a look at the valence electrons for all of them, notice how they're all 10 inner electrons. There's 10 inner electrons. You can see that if you take a look at sodium here, you can see on this first energy level, there's 2 inner electrons, and on this second energy level, there's 8 for a total of 10. And so all of these are going to end up having 10 inner electrons. And so there we go, we can write the 10 inner electrons for all of them. And now what we can do is we're going to do the same thing where we're going to take the protons, we're going to subtract the inner electrons to figure out the effective nuclear charge that valence electron experiences. So again, for this first one, there's 11 protons, and when you subtract this, it ends up giving you 1. Okay. There's 12 protons here. When you subtract that, it's going to give you 2. Okay, so there's 13 protons here. When you subtract that, it's going to end up giving you 3+. And then look at the pattern here. Notice how it's the same as the row before it. It goes 1 plus, 2 plus, 3 plus, and if you want to take you want to predict what the next one's going to be, the next one should be 4 plus, because if you take 14 protons and you subtract 10 inner electrons, you get a 4 plus. All right, so I've completed that row there, and you can see that it goes 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, 6 plus, 7 plus, 8 plus. And notice how the columns, you can see the columns all have the same core charge. And if you take a look at potassium, potassium will end up having a 1 plus, and we're going to go through that in a moment. Calcium will end up having a 2 plus. If you were to do bromine, bromine is right underneath chlorine. The effective nuclear charge for bromine will be a 7 plus. And again, what we're saying is this is the effective nuclear charge for the valence electrons. I want to be very clear about that, because even though, let's take a look at calcium, even though calcium, when we calculate the effective nuclear charge, it will be a 2 plus. However, that's for the valence electrons, but what if we were to think about this particular inner electron? If you were to think about that particular inner electron on the very first energy level, there's no electrons underneath that. There's no electrons underneath that that's shielding the nucleus. And so that particular one that I circled here will actually experience a 20 plus. It'll experience a 20 plus effective nuclear charge. So the reason why I bring that up is, again, what we're talking about specifically right now is valence electrons. And so that's what we're going to consider when we are doing this. So let's go ahead and do this last one here. There's 19 protons here. There's, if you count all of the inner electrons, there's 2 on the first energy level, 8 on the second, 8 on the third. That's a total of 18. So we subtract 18 electrons, and what you end up getting is you end up getting a 1 plus. Again, just like everything in that first column there. And then you can probably guess what this next one's going to be. It's going to be a 2 plus, because again, there's 18 inner electrons, and what we end up with is a 2 plus, like that. Okay, so again, just to kind of tell you where we're going to go, how does the force of attraction of this one compare to the force of attraction of that one? Well, the force of attraction for the valence electrons of boron have a greater force of attraction than that of beryllium. And the reason why is because there's a larger effective nuclear charge. And so notice as we go across the periodic table, there's a larger effective nuclear charge. But what about if we talk about this one here versus this one? So we talk about like beryllium versus magnesium. Well, notice how they have the same effective nuclear charge. They both have a 2 plus. So which one experiences a greater force of attraction? Well, the magnesium, the valence electron on the magnesium is farther from the nucleus. So again, the valence electrons are farther from the nucleus, which results in a smaller force of attraction. And so that's going to be the important concept to know moving forward. So as we go down the periodic table, they have the same effective nuclear charge. However, the distance is increasing as you go down, resulting in a smaller force of attraction. And so again, we're going to be coming back to this principle here, where if we have this situation, this is going to be a larger force of attraction. However, if we have this situation, where there's the same charges but different distances, this is going to have a greater force of attraction. And I'll let you go ahead and answer those 2 on the bottom here. What is the relationship between group number and number of valence electrons? The relationship between the group number and the number of valence electrons is the same. In fact, the effective nuclear charge, if you take a look, is the same as well. Notice how these have 4 valence electrons, these have 5, these have 6, these have 7, and notice how that happens to also equal the effective nuclear charge. And then what is the relationship between group number and the charge on the atomic core? Again, I just answered that, it's the same. The valence electrons happen to also be the core charge, which it's not saying that valence electrons are core charge, it just works out mathematically that they're the same. So definitely look over this, think about the pattern, and start thinking about how these electrons are attracted to the nucleus, and which electrons will have a stronger force of attraction, because that's going to be the key to understanding these next videos. Hope you have a great evening, and email me if you have any questions. Have a good day.